Questions about anything from last time or anything? Well, last time was a biggie because it showed that Fourier series converge to the function, the desired function, at least under the conditions that f is C1 smooth on the whole real line. That means that it's continuous and its first derivative exists and the first derivative is continuous. In that case, we get pointwise convergence. And the calculations that led us to that conclusion, I've summarized there. The partial sum of a Fourier series, that first sum is the real version, and that's 100% equivalent to the partial sum in the complex notation, which is shorter and sweeter to write and will be useful to us. And in fact, the complex sum is what allowed me to sum those up like a geometric series and get the famous Dirichlet kernel. So when I wrote those all out as an integral and put it all together and summed up the Dirichlet kernel terms, I got that formula involving the Dirichlet kernel at x minus t times f of t dt. And then because if I have an f, if I don't have an f that's 2 pi periodic, I can always extend my f as a 2 pi periodic function. Then I have a 2 pi periodic function, and then I can do a change of variables. I let a tau be x minus t, and did a change of variables and got a better way to write that thing with a dn of t. That's what I wanted. And then when I use the fact that the integral of the Dirichlet kernel is 1, and I can write f of x as f of x times 1, and then put the f of x inside the integral, and look at those two blue things. They're very similar. And it allows you to combine them and analyze the error. So, big step last time was I was able to write the error for the sum of a Fourier series as an integral. So Sn of x minus f of x is an integral from minus pi to pi of the Dirichlet kernel times something that looks kind of like a difference quotient kind of thing. But of course there's nothing in the denominator, so it's just a difference. And then I put in, so this is just a summary of what I did last time. I put what the formula for the Dirichlet kernel in terms of well-known functions, the sine function, and look at that for a second. I'm going to slide that sine t over 2 underneath the stuff in square brackets. And that thing in square brackets is 0 at t equals 0. Then it would just be f of x minus f of x. That's 0. So in fact, L'Hopital's rule is going to allow me to say that that function, even if I divide by sine t over 2, is a nice function. Okay, so I move that sine t over 2 under that, and I'm going to call that thing g of t. And I pull the 1 over pi out in front of the integral, and I move that 1/2 in. So this 1/2 right here, where did it come from? It came from here. Okay. And now I'm going to use the sum of angle formula, sine of nt plus a half t. I'm going to use the sine of sum of angles formula. The first term in that is sine nt times cosine t over 2. Okay, those are the green things there. That's the first piece of the sum of angles formula. And then the second piece is cosine nt times sine t over 2. And this t here, that 1/2 I put the pi out in front, and I put the 2 here. And of course the pi out in front also goes here. And the 2, in this case, goes here. So that's where those came from. And now, fascinating thing to look at this. If we know that the things inside the square brackets are nice, then we look at that first thing and say, aha, that is the real Fourier sine coefficient for the function h of t there. Okay. And we know by Bessel's inequality that when a function is reasonably nice, the Fourier coefficients go to 0. So that's how we deduce that that term's going to go to 0. And then the second one is the cosine term. That's the cosine term for a slightly different function. But we also know, and that's also an even nicer function, I'll call that h twiddle. So the first integral is the bn coefficient for h, and the second is the an, the cosine coefficient for h twiddle. Okay, and so the fact was, when f is C1 smooth, then L'Hopital's rule there allowed me to see that that g is continuous and 2 pi periodic. And that means Bessel's inequality implies that those tend to go to 0. In fact, let's see, whenever g is piecewise continuous, and I mainly need piecewise continuous so that I know it's Riemann integrable. So those integrals make sense. All I needed in Bessel's inequality was that those integrals make sense. So that allowed us last time, when I used L'Hopital's rule, I could see that g was continuous when f is 2 pi periodic. So the Fourier series converges to f pointwise in this case. And we were going to ask today, how fast can we make it go? Questions about? That's just a review of what I did last time. Yeah?
Should the first integral be the an coefficient because
It's a sine term. There's a sine nt, and so that's what goes in the formula for the sine coefficient. Yeah, and the cosine nt is what goes in the formula for the cosine coefficient. Anyway, multiplying inside the square brackets by the cosine t over 2 and the sine t over 2, those are infinitely differentiable, nice, smooth things. So it's strictly g that we're concerned about the smoothness of g. Okay, so I was summarizing facts at this point. Other questions? So let's see, when g is piecewise continuous, note it can have jumps. G can have jumps. And we would still have Bessel's inequality. Okay, that's a nice thing to know. Okay, so we know this fact now. The big question is, what if f has a kink, like we had in the harpsichord problem? So that means that there's f has a derivative from the right and the left at a kink. This is a graph of f of x. Has a right-hand derivative at x and a left-hand one. They don't have to be equal. So perhaps not equal. And otherwise it's C1 smooth. So it's C1 smooth, and it's just that those derivatives don't hook up there. They're different. So f is piecewise C1 smooth. Well, then the interesting thing is what we did. We can do L'Hopital's rule from the left. So what happens? How nice is G of t? And remember, G of t was f of x minus t minus f of x over sine t over 2. Well, we can do L'Hopital's from the right and L'Hopital's from the left. What's the notation for a right-handed derivative? Is there such? It's like f plus or something, and f minus, with a prime maybe. I can make up my own notation. Anyway, you can do it from the left and the right, and remember the calculation was that L'Hopital said the limit. Oh, I'll just do this. The limit as x goes from. Oh darn! I have an x there. Let me call this an x naught. Okay, the limit as x goes to x naught from the plus side of the derivative, not of the derivative, of this thing. Sine t over 2. Remember I did L'Hopital's, I did more carefully last time, but on the top you get minus f plus, I'll put an r here for right-hand derivative. So f prime at x naught, and 2 times that, let's see, this would be a half on the bottom. So the 2 would go up on the top. That would be a cosine t over 2 times a half. Okay, and the one from the left is going to be the left-hand derivative. So let's see, I'll take the lazy way out and just copy this. And change this minus to a plus to a minus, and that would be the left-hand derivative. There's some notation I just made up. And they don't hook up. So what's interesting here is that G is still nice in the rest of the spots, but at the kink, G has a jump. So what we see here, G is nice, where F is, by nice I mean continuous. Where F is C1, and those things that hook up. At kinks, G has a jump. G has a jump, but at least it's a finite jump. Has a jump. That's okay. The Bessel's inequality still holds. Still holds. Okay, so the fact is, Fourier series converges at kinks too. So here's a theorem. Let's suppose that F is piecewise C1 smooth and continuous. So the worst thing that can happen is there might be kinks. So it's piecewise, C1 smooth, and continuous, and 2 pi periodic, like the harpsichord problem. Like the harpsichord problem. Pluck shape. Then the Fourier series converges to F. Pointwise. That's fantastic. And here's let's think a little bit about our harpsichord problem again. So remember what the Fourier series was. Let's see, so what did I do? I had this piecewise, I had the shape of a pluck shape here, and then I extended it to be an odd function, and then I extended that to be a 2 pi periodic function. Etc. So that's the pluck shape. That's piecewise C1, and it's continuous because at the kinks they hook up. So that's what I mean. Piecewise C1 means on intervals it's C1 smooth, and the derivatives have limits at the ends. And the only problem here is that those limits don't have to hook up, so there could be kinks. Okay, and remember, I actually computed those Fourier coefficients, and remember they were alternating. Let's see, what was it? The Fourier series. This is the f of x. So let's call this red thing the extension f of x. That's the extension, 2 pi periodic odd extension. And then, I forget what was my coefficient in front. Was it a 1 over pi or something? Darn. I wish I had that in front of me. I'll fix this in my... There's some kind of number that goes in front of this thing. So, this today we know f of x is equal to 1 over 1 squared times sine 1 times x minus 1 over 3 squared sine 3 times x plus 1 over 5 squared, etc., sine 5 times x. And I forget, there might be a coefficient in front which I'm forgetting about, but it doesn't change what I'm saying, really, etc., ... But here's something interesting to note. Those coefficients in front of the sine functions are absolutely convergent. So 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared. If I take a plus, that's, let's take 1 over up to 2n plus 1 squared. That would be less than all the sum, all of them. So let's see, that'd be less than the sum as k goes from 1 to that number, 2n plus 1 squared, 2n plus 1 of 1 over k squared. And that's a famous thing that you can analyze. It's a p-series. And so, in fact, interesting, Euler figured out that this sums up to pi squared over 6. No, it's not approximately equal. Well, it tends to pi squared over 6 as n goes to infinity. So that's an absolutely convergent series. And so the Weierstrass M test implies that that series converges uniformly. So let's see. I'll summarize what the Weierstrass M test gives you Weierstrass M-test implies that this series converges uniformly to something. The series converges uniformly to a continuous function. So that's a part of the conclusion of the Weierstrass M-test. When continuous functions converge uniformly, the limit has to be continuous. Today, we know pointwise it's f of x. So now we know that that function is f of x. So today, we know that function is f of x. That's exciting. Of course, that was a lucky thing. I was able to compute those coefficients and say, oh, that's a well-known sum of a series. This is sometimes called a p-series with p equals 2. P-series with p equals 2. The p equal 1 case is a famous sum that diverges. P equal 2 is a good one. And you can use the integral test to just, if all you want to know is that's finite, the integral test tells you that's finite. So the integral test implies that it's less than infinity. Okay, so let's see, how would I know that here's sort of a... Let's say you never heard of the Weierstrass M-test, and I had to show you why it's true. Why the M-test works. In case you forgot all about it. Well, let's see. If I took f of x minus a partial sum of that series, minus, let's say, the Sn of x. That would be, let's see, that would be the tail end of the series, right? So that we know that fx, I'll write it like this. I'll write f of x minus the sum of all of the terms. Oh, blast. I claim that this is the sum of the terms. I picked a kind of a crummy one. I'm going to say why the M-test works in a minute here. Okay, so I'm going to assume at the moment you remember how the M-test works. It turns out that this idea works when f is C2 smooth also. So here's something new today. If f is C2 smooth, meaning having twice continuously differentiable, and 2 pi periodic, on R, then the series converges uniformly to F. And it's just like this harpsichord problem thing. because of the Weierstrass M test, we'll have an estimate that the AN, absolute AN, is going to be less than a constant over n squared, and Bn is going to be less than a constant over n squared. And so the Weierstrass M test as above, as in the harpsichord problem. Okay, that's what I'm going to show you. And this turns out to be very straightforward. So here's the y. Integration by parts is going to allow us to do this. Okay, so f of x would correspond to, I'll use the complex version now, corresponds to a Fourier series. You might, if you think you can differentiate Fourier series term by term, that's wishful thinking. But we would think that it's hopefully going to be true that the Fourier series for f prime of x is going to correspond to what you would get if you differentiate that term by term. And that turns out to be a true fact. If I differentiate that term by term, I would get in, Cn would come out by the chain rule. And the second derivative, the Fourier series for that, turns out, would be corresponding to in squared Cn e to the inx. Okay. If we could use Bessel's, then over here, Bessel's implies the Cn's go to 0 if the function is C2 smooth. And exciting here, Bessel's is going to imply that that these things are going to go to 0. Let's see, that's minus n squared. Minus n squared Cn goes to 0. And that's a much stronger result. That means the Cn's go to 0 really fast. And in fact, let's see, note, a thing to note. If we know that n squared Cn goes to 0, then eventually it's less than something, less than 1. Then let's let epsilon equal 1. There is an n such that natural number such that n squared Cn is less than 1 when n is bigger than or equal to n. And so what we get is that the tail end of that series, the Cn's are less than 1 over n squared when n is bigger than the tail end of the series. Okay, so it's like Weierstrass M test. The tail end of that series converges uniformly. Okay. So if I show that that those Fourier series do correspond to the second derivative and first derivative, I'll be done. So let's do the first one. let's see. Here's Stein's notation, which is a classic notation. Notation from Stein. I feel like I'm slighting poor Charcarci all the time, but can't help it. Notation from Stein is that f hat of n, the nth is a slick notation. F hat of n is the nth Fourier coefficient for f. Okay, that's a handy thing to have because now I'm going to show the proof that the Fourier coefficient for f prime is going to be in times the Fourier coefficient for f, just like I promised in that first twiddle. Okay, it's a pretty simple calculation. Remember, let's say that the Fourier coefficient for fn prime would be, 1 over 2 pi, integral from minus pi to pi of f prime of n times e to the minus I n x. What am I saying? F prime of x e to the minus I n x dx. That's the definition of that coefficient. And now I can use integration by parts. Let's see. What am I going to do? I'm going to rewrite this as 1 over 2 pi. I'll put my e to the minus I n x here. And my f prime of x here, dx. This is going to be my u, and this is going to be my dv. And I'm going to integrate from minus pi to pi. And so let's see, if u is that and v is that, then of course du is minus I n e to the minus I n x dx. And v is f of x. And so integration by parts is going to yield 1 over 2 pi. I'll get u times v. Let's see, I'll write it. 1 over 2 pi u times v minus, let's see, that be evaluated between minus pi and pi minus integral of v du. And that's 1 over 2 pi. Let's see, what's my u? My u is minus I n e to the minus I n x times f of x evaluated between minus pi and pi that's big fat 0 because everything there is 2 pi periodic. So that's, I don't have to look at that anymore. Let's see, then I would have minus integral of v du. That would be, I keep my 1 over 2 pi, integral from minus pi to pi. V is f of x. What did I say? That was stupid. U is e to the minus I n x. Sorry about that. Now I got to write du. Okay, that's still 2 pi periodic. Both of those things, f and the e to the something there, is 2 pi periodic. So that's going to be a big fat 0. 0. And this one here is, let's see, the du, that's where I got to put minus in e to the minus inx dx. That's the du. And so this big fat 0 is because that function is 2 pi periodic. All of them. And so they're the same thing at plus pi as they are at minus pi. And then I get minus a minus when I pull this stuff out. And that's a plus. And I can pull the in out. I times n. And what's left is exactly the Fourier coefficient. Oops, I have a 1 over 2 pi. Floating along. And then what's left is the Fourier coefficient for f, period. Okay, I'm doing this with complex on purpose because it's easier than the real case. I'd have to do 2 integrals in the real case, but they'd work out just the same. Okay, and of course that is in times the Fourier coefficient for f. Check. And you can do it so when you do it again, once you do it once, you realize, okay, every time you do it, it's the same thing. So you can do it again. And when you do it again, then you get that the Fourier coefficient for f double prime is in squared. It just comes out again, times the Fourier coefficient for f. So check to that, too. And so that Bessel's inequality is going to show that the terms in the series go to 0 even faster. So here's what we know today. So today's theorem improved, I guess it's not improved, it's just different. Today's theorem is that if f is C2 smooth and 2 pi periodic, then we know it's C1 smooth too. And we know that C1 smooth means the Fourier series converges to f pointwise. So the Fourier series converges pointwise to f. And now we just know, we also know that the Weierstrass M test showed today that the Fourier series, so it's just like the harpsichord problem, converges uniformly. To a continuous function which must be f. Okay, so that means that if Johann Bernoulli could have shown that to his brother, they might have thought better of that whole approach to solving the vibrating string problem. Let's see. Okay, so what got me hung up for a minute reviewing the Weierstrass M test was that Fourier series are kind of weird in that they have sine and cosine terms. And I didn't want to get bogged down in notation. But I'll review it now. Let's see. Well, I guess maybe I should also remark that that same argument, the integration by parts, in the real case, in fact, you're going to do one of these calculations in the homework. So integration by parts also shows okay, we have an f of x which corresponds to a Fourier series. And guess what? If you did the Fourier series for the derivative, it would be term by term differentiation. So there'd be no constant term here. And here you'd have sum as n goes from 1 to infinity. Let's see, derivative of cosine x would be minus n an sine nx. And then here you'd have plus nbn cosine nx. And same thing, if you know Bessel's inequality, you'd know that now you know that the NANs would go to 0. So if f prime was nice, you'd get Bessel's inequality with sum of NAN squared. And so the ANs have to go to 0 even faster. Etc. So you can do it for f double prime again. Differentiate again. So etc. So that's, and in fact, you'd be more comfortable with that integration by parts because it'd be very much like freshman calculus. And if you wanted to demonstrate those integration by parts I did with complex functions, if you weren't believing what I did, you could always write them out in real and imaginary parts and say, sure enough, that's valid reasoning. Kind of like you did in your homework. Let's see. Something I'm not going to show you, but it's not a hard thing to do. If f is what's called Lipschitz continuous, and 2 pi periodic, on R, then the Fourier series converges to F, pointwise. And Lipschitz continuous means that f of x minus f of y is less than or equal to a constant times x minus y. And if I wanted to, I could demonstrate this to you. The thing is, when I would look at that g of t thing, the Lipschitz constant would let me show you that it has it's nice and bounded at the spot where you're worried about it being singular.
Is that true for every term x and y, or is it for all x?
Yes, for all x and y. And that C is a uniform C for x and y in R. So there exists a positive constant C, so that's the case. That's called being Lipschitz continuous. And if I was going to show you this thing, the proof, g of t is bounded. And nice enough, is bounded near x and continuous elsewhere. So it's Riemann integrable. I think I'll save my review of the Weierstrass M-test for next time. It's continuous elsewhere. So everything's fine. So in fact, I don't want to get bogged down in fancier proofs, but the Riemann, this is called the Riemann-Lebesgue lemma.
What is
G of t is that thing I started out in the beginning. It was that thing divided by sine t over 2. Yeah, so g of t here is f of x minus t minus f of x over sine t over 2. The Lipschitz condition allows me to say that that has an okay behavior as t goes to 0. It's not a hard thing to do. I just don't want to do it. I've done enough. I want you to get the feeling for it rather than the nitty-gritty details of all these famous theorems. But you'll find that theorem in fancier books. I think Stein does it, probably in the exercises. Yes, I wanted to mention the Riemann Lebesgue. G, not a Q. Or maybe sometimes called a lemma. Yeah, it's a lemma. So Riemann, the Riemann version, if f is Riemann integrable, then the Fourier coefficients go to 0. And the Lebesgue version is Lebesgue integral, same thing. Same thing except Lebesgue. Integrable, which is a fancier thing. There's Lebesgue integrable functions that you can't even make sense out of the Riemann integral. Okay. And we proved that when f was piecewise continuous using the Bessel's inequality. When f is piecewise continuous. Using Bessel's. But it's true in much more generality. In fact, the Lebesgue one is the most general one.